This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
So this is Paul Verschure with the Convergent Science Network podcast for the Barcelona Cognition, Brain and Technology Summer School of 2018. And I'm here with Yoram Vodovotz. Welcome, Yoram, to our summer school. You spoke about the inflammatory response, inflammation, and also how the body responds to that. So how do you think the notion of inflammation is informative with respect to questions around, let's say, control and how even the brain might be engaging with the body?
Well, thanks, Paul. I think that at some level, it is just natural to think about that a process that can be as destructive as inflammation needs to be controlled. So the organism is wired to be able to respond to cues to cues that can be dangerous with an inflammatory response, and maybe even cues that are just stressful, and then that has to be resolved, and reset and be available to be used again. And so, one thing that's interesting that we find is that inflammation is regulated at a very local level, at the cellular level, that does not immediately appear to require any kind of additional neural control. But at the same time, when we look structurally at the neural mechanisms, all evidence points to pathways regulated by the vagus nerve that are probably involved in sort of minute-to-minute regulation of inflammation, to the point that you can actually target that mechanism to improve or reduce the inflammatory response in fairly intractable inflammatory disease states, in a way that's much more powerful and potent than simply administering drugs systemically.
With that, now you already jumped to the conclusions before we even have done the introductory part, right? Because also in your talk, you indicated that in your view, inflammation is underlying maybe all diseases, or is involved in all diseases in some form.
Yes, right? I think so.
So it's a very global, but it would also meaning a very non-specific reaction of the body to a pathological perturbation.
I think one way to look at it in a kind of integrated way is to say that everywhere and all the time in the body, we need to respond to stressful or noxious or infectious stimuli. And that because we are wired to do that, it's possible sometimes that those control points will be insufficient or will be overly robust. And then that may be the real basis of inflammatory disease, or maybe all disease, if all disease has an inflammatory component. So in a sense, we can make the argument that it's failure of control that is what makes inflammation bad. Because within a range, inflammation will stay local. And when it stays local, it generally does what it's supposed to do. It's possible for it to become overly robust locally to a point, but most of the time, that is still compatible with reasonable organism health. The hypothesis would be that once either the stimulus is too prolonged or too big, or that there is a genetic variability that makes one over-responsive or unable to control sufficiently well, now inflammation spills over into the systemic circulation. Mm-hmm. And that's typically when we would say this is a disease, this is a bad outcome, right? And so then of course the corollary to that is that it is the brain and neural circuits that are now failing at their job to keep inflammation localized.
No, wait, we don't know yet whether this is neural.
We don't.
Because in some sense, we didn't even get to the point that we really defined inflammation. What does inflammation actually really mean? Because in some senses, it seems to be a phenomenon that is deviating from the standard, but it can occur at many different spatial temporal scales and also with varying levels of intensity. So how do we now really define inflammation? What's inflammation exactly?
So at a core level, I keep using the phrase that inflammation is communication. So I think inflammation is an intermediate set of pathways that connect the original insult or injury or deviation from homeostasis to some response to that, right? So of course, the typical control systems you're thinking of are neural control, and you're thinking of the nervous system as having that function. It probably happens on a faster time scale than what inflammation does, right? So inflammation is the communication framework, but now the problem is that the language of that communication can itself become the cause of the disease, or the aspect of the disease that becomes propagated or gets worse or cascades further and further out of control. So inflammation has this dual role, which is, or you could argue that it's an intrinsic role. The very fact that it's an intermediate timescale process, and that it uses molecules that can cross into, say, the neural system, but also into other aspects of physiology, set it up for this possibility that if things go out of control, the very act of communication becomes the detrimental thing. And now you may not even be able to find any remaining evidence of the original stimulus that started the whole process, the whole dominoes falling. You just see the dominoes are falling, right? So now the problem becomes that it's the dominoes falling that are your problem. And that's when people say this is an inflammatory disease. They focus on those mediators. In fact, they often confuse or interchange the term marker and mediator, so as if a molecule that is there in the body is doing nothing more than to act as a marker of something, right? Of course it's not. It's having a biological effect. So it's a mediator.
But if we now bring it down to the simplest form of, what's the simplest form of inflammation that would still qualify for that label?
I would argue the simplest form of inflammation can be seen in very primitive organisms, or even perhaps single cell organisms, where there's a stress response. So the response to anything like a chemoosmotic stress, even a lack of nutrients, or an overabundance of some stimulus, the molecules and signaling pathways that one can find are sort of a proto-inflammatory response, because those same molecules are typically implicated in doing something inflammatory. If you were to just give those molecules, you will see a response that you could argue is inflammatory. We did some of our studies. I didn't go to the lowest level organisms, but we did some studies on malaria, and we were looking actually at the mosquito host for the malaria parasite, and show that mosquito host is elaborating exactly the same types of responses that the human host does, right? So now this mosquito that is thought of as part of the problem in the disease, for carrying the vector, for being the vector for disease, you might say, well, it's not harmed in any way, it doesn't care, or perhaps it's even benefiting from transmitting this disease. But the reality is that it doesn't. It's fighting this disease tooth and nail. In fact, the disease would be way worse if it wasn't for the fact that this mosquito has done a quite good job of limiting the parasite burden in itself before it ever bites the host. And as a separate twist, the act of blood feeding, depending on the kind of host that it is, if that host is infected, there will also be inflammatory mediators that transit into and get internalized into the mosquito, and the mosquito recycles them and uses it for its own signal transduction to fight off the parasite. So there's this entire almost ecosystem type effect where inflammation is no longer about just what happens to the one organism, but it's about a cross-organism transfer of information.
So you would see it as originating already in single cellular organisms. So it's a very old mechanism.
Yes.
So it means if we want to understand it, we shouldn't start looking at complex multi-organ systems, right? You talk single cellular ones.
People are doing great studies in zebrafish, for example, because they're very amenable to perturbation and visualizable, in terms of fluorescence.
Should we start with E. coli or something like single cellular?
So people have, where they're, but they typically what they do is then they engineer the unicellular organism to be able to record what essentially it's doing and so forth. The problem with that is that if that's great if you're trying to come to the kind of evolutionary mechanisms and initial set of feedbacks and so forth. But because the problem with that approach, though, is that because we can show that it isolated cells from, say, people or mice can be put in culture and can exhibit this inflammatory response that has many features that we can see at the tissue and the organ and the organism level. The problem is that the two things aren't automatically dockable. Just because we can see it at the single cell level doesn't mean that we automatically understand the way inflammation is really, really regulated, because normally you will never have any of our cells just sitting there by itself. It's always going to be in the environment of the entire organism. So, it's a teleologic argument. Are you, maybe what you really need to understand is the entire organism and control as a system to infer the core features that matter there and see which of those features can still be recapitulated at the individual cell level.
But at the bottom, would it be fair to say that it is linked to the homeostatic functions of the single cellular organism, and that maybe we should then limit it to the very specific homeostatic functions that Maturana and Varela called autopoiesis, which is it is the homeostatic function that allows the self-maintenance of the organism, right? So it's not just necessarily taking care of your energetic status, but it's really about the integrity of the organism itself. And as soon as that control loop starts to become perturbed, that's when we start to see inflammatory responses.
Right.
Would that be reasonable to really link it to autopoiesis in that sense?
Yeah, I think one interesting application of that would be to help define thresholds. So like for particular pathways, defining which ones perhaps are the original ones or the closest to the original ones. What were the original actual functions, and seeing whether those functions are recapitulated at higher orders of organization. That I think would be very good. I think being able to, as you said, help define what are the actual interactions that cross a threshold from being normal everyday housekeeping to being something that's now, quote, inflammatory. I think that would be quite useful. It is very interesting that you talk about metabolism, because now, of course, we're appreciating that metabolism and inflammation and immunity are highly linked. So T cell functions, macrophage functions, other inflammatory type cell functions are very dependent on metabolic fluxes, and of course end up regulating metabolism.
Right.
So,
but now if we go from single cellular to multicellular, let's say we go to a slime mold or something simple, would you see that when a slime mold is the response of this collection of cells that make a slime mold already qualitatively different in case of inflammation than the single cellular organism? Does a slime mold start to do different things?
I think the slime mold starts to do different things, because now there's an entire additional set of functions that come along that need to be optimized as a necessary function of that additional cellularity. So there's a cost to maintaining that additional cellularity. There's a greater distance. There's a greater need to have nuanced timescales of response, and now one might imagine that there's additional, of course, biological pathways that come along with doing that, and so then that system has to be synchronized. And so, but yet, if one identifies what one might imagine are the core functions, those functions still have to be retained. Right. So now how do you propagate from the single cell to the multi-cell while still retaining the overall qualitative behavior? Right. That I think is where the really interesting insights will probably come along, because that might actually even speak to how each step of evolution necessitated an additional set of new branches that together had to be synchronized to achieve a macroscopic behavior of the entire system.
Right.
Yeah.
So if we go now to the multicellular organism, would you see the reaction? So, for instance, temperature change is a typical expression of an inflammation, right?
Yes.
Is temperature change also something that a single cellular organism would display, or that a multicellular organism will display?
No, I mean, they're going to be dependent on their external environment, but they may very well respond differently, and they do, in terms of the temperature. So this whole heat shock response is intimately intertwined with inflammation. Mm-hmm. So heat shock proteins are actually a prototypical category of these damage-associated molecular pattern molecules, or DAMPs as we call them. So they are molecules that do various housekeeping functions in their normal context, but when present in abnormal context, either in the wrong place or at the wrong time or in the wrong context of additional molecules, now become sensed as danger or alarm. And so again, another interlinking between the environment, sensation of the environment, and adaptation to the environment, and inflammation, right? So again, comes back to this thesis or hypothesis that inflammation is communication. Mm-hmm. Because at the end of the day, inflammation isn't a thing in and of itself normally. It's just a way of transmitting the information from a beginning to the end. It's just that when it rises above a certain threshold, because it's now intertwined with so many other pathways, inflammation now becomes the causative agent. Or inflammation acquires the word becomes the word inflammation.
Information. If inflammation is information or communication.
Yeah, you could say it's information, or you could say it's communication. It's sort of similar.
Too non-specific, because in some sense anything is information if you want, right?
Right.
So,
but not every single thing that's information can become causative for something that is pathological. So
yeah, but if we would agree with this earlier definition of autopoiesis, self-maintenance of the organism as a system, right? This would require forms of communication between constituent components,
right?
But in the end, isn't it more a form of actuation, to set in motion certain reactions at the lowest level, certain biochemical processes, right? To assure maintenance of the system.
Yes. No, I would imagine that in a lower organism, it's perhaps more actuation, because you're already a single cell, and so you don't really need to communicate. Although perhaps you communicate quorum sensing, or in a sense you're communicating to nearby cells. That's possible. Communicating a sense that use your flagella to swim away from this and towards that, or whatever. But yes, I think at some very basic level it is actuation. And then you could imagine that as you move up the evolutionary scale, that actuation becomes subsumed into a set of biochemical pathways where they don't directly create motor actions in any given direction or another, but actually transmit biochemically the sense that something must be done.
Okay.
Yes. So if you say transmitting that something must be done is actuation, then I'm perfectly okay with the word actuation. Yes.
So this is cool, right? Because now we have a foundation also look at these more complex forms of inflammatory responses that you might find in multi-organ systems and so on, right? So and now you indicated, so because we also want to look really a little bit at how does this possibly relate to the neural control of inflammatory response. And of course, brains start to emerge when you have to coordinate across multiple parts of a system, right? That cannot necessarily at a direct signaling level exchange information, because they would not have the signal capacity, right?
Right. It's too far apart, right? Yeah, exactly. Yes, yeah.
Or there might be transduction delays that you have to overcome and so on, right? So the brain starts to get involved as soon as you have a multi-component system, multi-organ system, if you want, where you have to coordinate across these systems.
Right.
So that would suggest that whether we talk about the skeletal muscle system, or you talk about, or use the muscle system to control if you're a worm, or we talk about regulation across the inflammatory responses of subsystems, right? So how do you look at that? Do you see it like every subsystem has its own intrinsic inflammatory response? So there's a perturbation, there will be an automatic reaction, predefined, genetically tightly controlled, that then has to be regulated yet again by either an immune system or a nervous system, right? So how do you see that these three components work together?
So I think that it's actually sort of both. So you have the organs, the typical organ structure, or let's call it, let's say even at some level, a tissue, is the structural or functional cells or parenchymal cells that do the job that differentiates this organ from being this other organ, or this tissue from being this other tissue. Typically interspersed among them are these resident inflammatory cells like macrophages and others. And then typically touching on them are nerve termini. So we can observe that the tissue in some sort of isolation will exhibit this inflammatory response. But we also exhibit coordination across tissues or across organs, right? And so for example, in some fields, people talk about the gut as the motor of inflammation, right? And of course, the gut has got its own innervation. It has a sort of primitive brain. The gut is quite central for many reasons in coordinating responses, but the brain is controlling the gut, right? So the gut can do its own inflammation. The liver can do its own inflammation. The lung can do its own inflammation, which makes sense, especially the lung, for example. You're breathing in particulates, though some of those may also be pathogens that you're breathing in. You have to be able to deal with them locally. Mm-hmm. And presumably you have to send information that you're dealing with them locally to the brain. And then the brain kind of keeps tabs on this and says, okay, is the branch office doing a good enough job of dealing with this, or do we need to involve the head office? Mm-hmm. But it's not that you wait necessarily, I would think, until the problem is out of hand at the branch office. You're sort of keeping tabs, right? And then at some point, that is also the act of keeping tabs at the brain level, presumably, is also activating pathways in other organs for whatever appropriate reason, either for a need to further ramp up, or because, for example, a pathogen can evolutionarily have been anticipated to move from one organ to another through the blood or through the nervous system, right? So the threat is evolving dynamically, and so then the system is kind of doing its best guess at how to evolve dynamically, right? And as long as it's all under control, mm-hmm. the threat or the damage is dealt with in some fashion. It's contained, and then there's a time. There's an element of having already from the beginning started some anti-inflammatory, meaning stopping functions, and also these same functions are pro-healing, and so you're beginning the healing cascade as you go. If it all works out great, everybody at the brain level kind of congratulates themselves that the crisis was addressed, and then some amount of time later, the tissues return to some sort of homeostatic state that's compatible with life as a system. But the problem becomes, I think, when either the threat is too large, it moves too fast, it persists for too long, or because of the other evolutionary trade-off, which is genetic variability that we have to have, you have a particular organism whose genetic variability makes him or her that much more prone to respond. I think more prone to respond to assess damage and think I have too much damage or more damage than I actually have, or I have more stress than I actually have. That's often tied to pain, right? Pain is very subjective. Mm-hmm. There isn't any clear molecular correlate of pain. It's something that you have to kind of assess subjectively, and coincidentally, of course, that is very much a nervous system phenomenon. So it's very possible that an organism is at a genetic level somewhat overly sensitive, or potentially the other way around, not sensitive enough. Right, but you need that range in the population to just evolve. So then you need it in the population, which means that individual will now become sick. That inflammatory response will progress further than it ought to. And now that can lead to all kinds of detrimental consequences. You could imagine at the farthest end, evolutionarily speaking, that if it's incompatible with life, the damage is too much, this organism dies. Those genes, presumably, are not passed on. An editing process has occurred, right? So inflammation even subserves that role. You know?
Yeah, but we moved a bit fast now. So if you take the example of the lung, right? So, okay, I have particulate matter that enters the lung. It triggers an inflammatory response. Now, who wants to know about that for what reason, right? If we take this sort of more anthropomorphic perspective, before even the brain starts to worry about this, which other organ would even care, right? The heart might care because, okay, lung capacity is going down, so I got to pump harder. So I want to know about this as an example.
Yes.
So in that sense, in terms of, if we get this perspective of maintaining the integrity of the whole organism, who wants to know about any kind of perturbations at the level of the lung?
Well, at some level, if you're in an environment where you're breathing in toxic materials, you might need to actuate functions that, that activate a program to move you away from that environment, right? A kind of survival program. This is a noxious environment. I need to move. Those functions are already there, right? At some level, the brain is already doing that. But maybe that's not for such a rapid and massive change that says, I'm living in, all of a sudden I've been put into a very low oxygen or a very high CO2 environment and I need to propel myself out of there. I may be in something that's a more slowly evolving thread on that time scale. I'm only finding out about it 3 hours later, right? And so then maybe that triggers a sensation that you need to get out of there and go somewhere else. But of course, other organs in the meantime are also going to need to be responding to adjust their physiology appropriately to this new load. You cannot do what you were doing before because you're also dealing with this additional particular or pathogenic burden or some other type of damage. I now need to compensate around that. A key one obvious one is in following injury, you may have severe bleeding. A key inflammatory mediator, interleukin-6, activates the coagulation cascade. So you're rapidly activating a coagulation cascade to close up that hole. Of course, the problem is that the coagulation cascade now feeds back and activates more inflammation because, I don't know if because, but at least you can speculate that if you have a big hole in your body, the next thing that's coming is a massive wave of bacteria from your own skin or from the environment or whatever. So there's going to be an invasive pathogenic opportunity there from that hole, right? It's not that the body is sensing the hole necessarily, but it's sensing that there's a blood loss, which must be due to a hole, right? So now you're activating a pathway of coagulation, and perhaps it's disseminated, which happens in multiple places. Perhaps because, again, it's preemptively coagulating because bacteria will probably be entering, and so they'll get to various places, and so now you need to coagulate to create barriers to trap these bacteria. That coagulation is pro-inflammatory, again, because you need to wind yourself up for the eventuality that you might have a pathogenic fight on top of your traumatic injury fight. If all of that gets spun up too much out of control, because there's an inherent, very strong positive feedback, you could imagine in a setting that's not supported by modern medicine, that's now no longer compatible with life. And so then the organism will die. And even that's good because the organism's death means that organism's not transmitting the pathogenic agent to the rest of the population. And if it's a trauma and not with a pathogenic population, well, that organism is not bringing the predator back to the rest of the population, right? So even at an evolutionary level, you could imagine that this is actually something that's beneficial evolutionarily.
But that means for these multi-organ systems, there are predefined response patterns, as you now described them.
Yes.
Right? So how big is that repertoire, you think?
So you're talking about the organ-specific response pattern. So yeah, we've addressed some of that by trying to look at a defined panel of inflammatory mediators that interrogates a broad array of inflammatory and immune pathways that are known to sort of be interlinked. And when you do that, and you do that in response to sort of a prototypical stimulus, which is sort of one molecule derived from bacteria that is a known potent immunostimulant. So you're using that as a sort of prototypical system that you can control and you can actuate quantitatively. you do find quite different dynamic responses in an organ-specific fashion. You can kind of, on depending on the tools you use, you can quantify peaks and valleys in this dynamic process and begin to think that there is a sort of programmed temporal wave or spatiotemporal wave of this inflammatory response, and that it is presumably happening that way for some evolutionarily conserved reason that relates to the likelihood that that specific pathogen is what you've got, and the pathways by which that pathogen may disseminate, or the locations to which that pathogen may go and cause very serious harm versus not so serious harm, are those ones that are responding sooner versus later, and so forth. Of course, those are all hypotheses to be tested at some point.
But the way you describe it now sounds like a large chunk of the inflammatory response is relying on these predefined response patterns at the organ level.
I think so. I mean, because it, at some level, the organ is a compendium of its cells, right? Even if we took the potential for neural control now, okay, because the alternative or the related, not necessarily alternative hypothesis is that the reason or that we see these organ-specific patterns is because of the way neural control works. Which regions of the brain activate first, second, third, and where do they project, and where does that response happen? At some level, I think it's a semantic argument. My guess is evolution would not have gone that way if it wasn't beneficial to activate inflammation in a particular sequence.
Right.
I would guess. But at some level, an organ is a compendium of the cells that it has. Some organs have a greater proportion of sort of their parenchymal cells relative to their resident inflammatory cells than other organs. A prototypical organ is, again, the intestine, the gut. Of course, we all know the gut is really the outside of the body at some level, right? So, of course, in the lung as another one. So these are surfaces that are directly, essentially, in contact with the outside world. It's not illogical to assume that these are ones that need to be very finely tuned in terms of how they regulate their inflammatory response, because you are constantly impacted by the outside world. You can't have a situation where you're constantly inflaming out of control and having all of your organs kick in for any stimulus that comes along. There have to be very high thresholds that have to be exceeded in order to really get the cascade flowing downstream. There's other organs that are obviously more internal, that if they come into contact with a bacterial-derived immunostimulant molecule, the interpretation must be there's bacteria already inside, right? They're already present. They already have made it through the barriers. So activate right away, right? You could imagine that would be the program. And there's some seminal papers about gut inflammation, the ones that define some of the prototypical actions and regulation of the key signaling pathways for inflammation, like NF-kappa B, that show that the gut is sort of wired like that. It's pretty much stepping on the brake pedal until a fairly high threshold is exceeded, and then the foot is lifted off the brake pedal, and that creates motion. Now there's a response. Other organs have got the foot much more lightly on the brake pedal. Yeah.
But now what you call the inflammatory response, if I compare the inflammatory response in the lung, how is that different from the inflammatory response in the liver or the spleen or the heart?
I mean, the molecules that evolve, they might evolve at different times depending on thresholds, but they're often very similar. There are some molecules that are more present in certain tissues than others. Often when people say inflammatory response, they sort of are mixing the terms and are talking about not just with inflammation, and meaning the direct molecular actions being driven by the direct molecules that we can say are inflammatory, but then sort of the secondary phenomena. So for example, edema, so in the lung, you will have lung edema. You might not have it quite as much in, say, the liver or something like that. Or the gut, right? So it just depends on the secondary function that or dysfunction that becomes triggered is often also very organ specific. But I think that the actual mediators that one finds are often a fairly well-ordered cascade of mediators. They're typically the earliest responses, let's say to a tissue injury in that particular organ, are going to be these DAMPs. After that is a class of these cytokines that we call chemokines. They typically are there to help attract circulating inflammatory cells to the local area, but they actually have many other functions. And then the classical cytokines, right? The problem is it's not like the first thing, then you wait a while, then the second thing, and then you wait a while, and the third thing. These networks organize very fast. And then the next behavior that is very interesting is that they organize very fast across multiple tissues, where you begin to think that the only way that could happen is if there was neural control, right? Because how else can you explain a situation where a leg is broken severely and already the gut is beginning to have a problem, right? Is beginning to change its inflammatory profile. And then let's say the liver and then the lung. These distal responses that are sensed almost immediately, right? That cannot happen just through simple diffusion. Yeah.
So you mentioned this model by Namas and others, where they actually distinguished sort of three profiles of the inflammatory response, right? Where you talked about, let's say, an adequate response, where you remain within the range, which is still supporting the integrity of the organism. But there you were making the point, it never returns to baseline. You always change.
Yes. You're always not just change, you're typically worse off. So you're leaving behind traces of inflammation. You're not simply completely resolving and coming down to baseline.
So the additive is something.
And which means that the next time that you get hit with a stimulus, you're already being hit not at a baseline of 0, but at a baseline of +1. And that is why preconditioning, studying preconditioning and mathematically modeling preconditioning have been activities that we've been very interested in since the beginning of this process, because of course you're never naive. You've never been exposed to only one thing. By definition, you've already been exposed to a bunch of things by the time you're exposed to whatever it is that you're studying, whether experimentally or clinically.
So that also means, also from a clinical perspective, the response to, or the inflammatory response of every individual patient is uniquely different because they are at a different set point.
Exactly.
Right.
It's all the prototypical complex system. Initial conditions are perhaps the biggest single determinant. Right. Yeah.
Okay. And then you also mentioned that either you can have an excessive response that exceeds some threshold, right? Or you can have, let's say, an hypo-inflammatory response that is sort of more reduced than expected.
Right.
And in both cases, you're outside of this envelope that would sustain the organism, right? So why is that significant? So in both, is this distinction really strongly supported by empirical evidence?
Yeah. So we have in one sort of clinical system that where we think we can get that where we've made many of these insights, which is severe traumatic injury. In a large population study, observational study, where, in approximately 500 patients, where we could, first of all, interrogate a broad array of injury severity. So it wasn't just focusing on the most severely injured patient. It was really a survey across injury severities, which was very important because you could see the entire envelope of responses. And over a pretty long period of time, we could find subcohorts of these patients that exhibit these phenomena now. I mean, the original picture that you described was a hypothesis. It was derived from, let's say, let's say clinical experience and maybe experimental experience where there's a sense that this is what happens. But with being able to actually measure the mediators, create dynamic network representations of those mediators, we can in fact point to cohorts of patients and circumstances under which we see each piece. So for example, if you compare highly matched patients that went on to live versus went on to die, sort of the biggest bifurcation you can have in anything, but of course in trauma, you can see the sense of self-sustaining inflammation with networks complexity that rises and rises from pretty much as soon as you can measure, versus other networks that look sort of flatlined and just not responsive at all. That's one case. We have patients that have a phenotype of coagulopathy, so they're just not coagulating appropriately, or then later on they're overcoagulating. And when you look at them, they also, compared to highly matched controls that don't have that phenomena, look like they have just an insufficient inflammatory response. And then if you, again, to bring it back to the brain, when we compare the networks of patients that have a spinal cord injury versus highly matched patients from similar with similar injury characteristics, but that don't have that spinal cord injury, we now again see this hypoinflammation. So there's clearly situations that whether they're all related to each other. I mean, for example, the one inference would be that if a spinal cord transection gives you this profound hypoinflammation, is that relevant for anybody that doesn't have spinal cord transection? Or does it mean that those patients have some degree of neural dysfunction, right? Our hypothesis is that we're looking at patients, when we see patients that have this hypoinflammation, that they have some degree of neural dysfunction. Now, what type of neural dysfunction, I don't know, but we can potentially suggest some biomarkers, inflammatory biomarkers that appear to be hallmarks of that. Likewise, in the case of the overly revved up, overly stimulated, overexuberant inflammatory response, again, we can have biomarkers that go along with that, and they're different. So, yeah, the suggestion is that different programs have been set in motion. And
that hypothesis for the spinal cord lesion case is that as soon as you detect that the blood-brain barrier is compromised, you actually want to reduce the inflammatory response to prevent any from these signaling molecules actually enter the nervous system. Because
that's a terrific hypothesis.
The cost of that will be huge, right? Because then inflammation hits your nervous system, and that might be the end of a lot of things.
So the whole concept of a kind of hibernation or stasis that as a protective mechanism, and I think is absolutely key. And I think there's many links to inflammation playing a big role in communicating that and mediating that. Yeah. Right. So I agree. That's a terrific idea. Yeah.
Okay. So now we have the sort of three ranges of responses to inflammation, which clearly points to this being a control issue. This has to be, this is a controlled response, but the control can be sort of showing too much positive or negative feedback.
That's right.
And also you mentioned in your talk that you see this inflammatory response very much as an interaction between positive and negative feedback loops.
Yes. I mean, obviously that's a fairly straightforward way to look at any complex system, but we've developed a set of sort of, let's call them proto-interactions, if you want to think about them, the functions that might have been there at the earliest stage of evolution that we can play forward, we can encode them into mathematical models, and we can reproduce a range of both qualitative and then quantitative behaviors. If we code that set of interactions with that key tug of war between positive versus negative feedback into agent-based models that are, say, spatially realistic, we can reproduce patterns that we see in real human microscopic sort of histology or even macroscopic lesions. And so that doesn't automatically prove that we're right, but we've been able to make those leaps because we base them on that core set of hypotheses of these specific positive versus negative feedbacks.
But I think there were two really interesting consequences of that, right? Because you were saying, well, it's not just sequential. At first I'm ramping something up and then I'm ramping it down.
Yes.
It's very much that positive and negative feedback are operating in parallel.
That seems to be the case.
I think that this is rather an important insight, but the question would be, of course, what's the advantage of that? Why would you do it that way?
Yeah, so it's been very interesting to think about why it is that such a system would have evolved that way. You could imagine that that's a way to give you much more fine-grained control, more rapid control, more nuanced control. I also think that at some level, the body or the organism has to sort of, its baseline state has to be somewhat anti-inflammatory because of the fact that so many perturbations will be pro-inflammatory. So the baseline state is not zero, but it's actually trending towards anti-inflammation. So for example, let's take something simple. Muscle stretching as a function of just daily activity, walking, within a range, nothing severe, nothing athletic, nothing stress response, fight or flight. You're just walking, dealing with normal activity. we did some work in collaboration with other investigators that you can replicate that as cyclic stress and cyclic stretch in a cell culture system. And what you're seeing is a tonic elaboration of key sort of anti-inflammatory pro-healing mediators. Now, simulate a much more dynamic process, exercise, sort of fight or flight, need to run. Now you're stretching faster or bigger sort of amplitudes. That entire regime switches over to activation of pro-inflammatory pathways.
Mm-hmm.
So the point is that the system will never know when it needs to switch from being just doing its normal amount of movement, if you will, to the needing to instantly need to run. And you can't trade off evolutionarily. You can't be always inflamed on the off chance that you might need to become more inflamed. And so then you need to basically have this available bifurcation at almost every time step. At every time step, you need to be able to choose to go to the right or to the left, to go to pro or to go to anti.
But not inflamed would mean at the level of the tissue, really a zero expression of any of the markers of inflammation, or just a low expression of these markers?
I think that we get a tonic expression of key anti-inflammatory mediators. I think sometimes we can find what look like baseline levels of pro-inflammatory mediators, but they often are there because they're also subsuming other physiologic functions, or the experimental situation, we cannot ever truly demonstrate that we didn't create some stress in the process of creating the experiment to look. So there's always that kind of Heisenberg uncertainty, the fact that we're observing it is creating the situation that we're observing. So,
but now in terms of the negative feedback, is a negative feedback an expression of anti-inflammatory mediators or a suppression of the inflammatory mediators, or both?
Yeah, so this is a big argument in the field right now, and I don't know if some of it is semantic or if it actually is a specific thing. People talk about resolution, inflammation resolution. You will see this word coming up in many papers, and these are very good, very respected investigators. There clearly are entire programs whose job it is to resolve inflammation after the fact. I think that those are related but distinct. I think there are two levels. There's the level of control and decision-making, some of which can stretch out to a longer period of time, and then some of these same mediators can drive secondary functions that are pro-healing. And then there's the actual longer-term process. So it's a well-known feature of wound healing that you can sort of shut off that initial inflammatory phase, and you can even begin to heal a tissue over the next longer time scale. But to truly remodel all the way back to something like what you were before the injury takes a very long time.
Mm-hmm.
So but you were able to kind of, put a Band-Aid on the problem, and it just takes a while for the problem to fully, at least achieve enough of a scar or whatever to further shore up that repair. There are many aspects of healing after injury that don't have that skin wound healing kind of vocabulary, but it's that same basic idea that you need to kind of shore up the broken or disturbed tissue so that it can go back to doing at least some aspect of its job, and probably to turn off signaling that tells other organs that there's a problem. So you kind of quiet that whole thing down. And then once that's done, you can give some time for the resolution processes to really just do their job. I think that when you're looking at chronic inflammatory settings, which, as I mentioned in my talk, I think is more like a chronic restarting of acute inflammation. Now you can see these active resolution processes, but that's just a function of the dynamics. Because you're constantly restarting, you're never fully healing, then you're seeing a resolution program that needs to kick in and stay on for a long period of time. Right. And then you can call that now a resolution program because it's tied to the resolution of inflammation.
But if your explanation of chronic inflammation as the result of starting up the process of acute inflammation, but just doing it repetitively, that would suggest that some time scale you should see transients in the chronic responses. So is that the case?
I think it is now that people are looking. I think that often there is an inherent sort of, let's call it bias. You make a hypothesis, and the hypothesis is geared towards, let's say, looking at arms of the response that are downstream. Well, then, of course, you're going to be seeing the arms of the response that are downstream. this is why systems approaches like the ones we do are, I think, very necessary. So because we interrogate we stay agnostic and we interrogate the entire process all the time at every time point that we study, we have a chance, an opportunity to actually see mechanisms that are acute being turned on. We also see the reverse phenomenon. We see a very rapid activation of processes that are thought to be more chronic. Mm-hmm. But again, they're in the context of also processes that are very acute, which I think is just a part of the hallmark. Right. Yeah. And I mean, the building of dynamic networks or network representations of these are also key because people tend to focus on single mediators. So you measure 30 mediators and you say, okay, I'm seeing a program. But of course, in order to say that you're seeing it, it has to pass a statistical test. And if it doesn't pass the statistical test, then you're not seeing it. But if you look at it as a network, you all of a sudden find that it's there. Right. So, but
also, if you look at this interaction in the positive and negative feedback loops, there you also then distinguish a predefined component and a more adaptive component.
Yes.
So who's the mediator of the adaptive component?
So the adaptive components are, I'm assuming that you're meaning the cells and the mediators that are characteristic of the adaptive immune response?
Yeah, like T-cell mediated responses that you mentioned.
Right. So they have so some of the mediators are shared. So T helper type 1 or T helper type 2 or now, TH17, and there's many other subsets that have evolved, but let's just for simplicity's sake focus on the TH1 versus TH2. There's a set of mediators that are also being made by innate immune cells, but that happen to serve the program of driving the differentiation of, let's say, specific subsets of T cells that have fairly specific T cell receptors that, say, for example, might be specific for the particular pathogen you got infected with, because it is efficient in the face of a long-lasting infection to focus on just that infection rather than a generalized alarm that impacts many bystander cells and many other systems negatively, right? The initial response is fairly nonspecific, and there's a trade-off, which is you're damaging your cells. The trade-off, on the one hand, is a necessary price to pay, but on the other hand, it's part of the amplification loop because the damage that you're doing to the cells produces these damps, which further amplifies, and so it's part of the structure. It's actually not just bystander damage. It is bystander damage, but it's also bystander damage that is part of the structure of the system, right? So that's okay within a range, but now after a certain point, you can't tolerate that anymore. The signaling aspect of the damage becomes secondary to the actual damage part of the damage, and so then you can't keep that going for nonstop. It has to sort of segue to something else. So the system is already building up the potential to become focused, but you don't want to become focused too soon because that isn't intelligent. It's the equivalent of what happens in the vaccine setting. We vaccinate for flu. It's the wrong strain, and now we have no protection, right? We force the system to go in a certain direction. A vaccine is nothing more than an adjuvant, which activates the innate immune response, and the antigen part, which activates the adaptive part. But the system is a cascade working together. So we force it to go in one direction with the vaccine, but maybe we forced it in the wrong direction. So now we have too much of a response for exactly the wrong thing, and now the vaccine is not functional. But the thought is that it's still better than trying to do it by random coincidence and just activating the pre-existing clones that you have for that specific infection. But absent modern medicine, that's how you'd have to do it. You would have to, as soon as possible, but not too soon, segue over to a response that's as focused as possible to the actual problem that you have. Right.
So does that then also explain or at least suggest why at some point you have to bring in the brain as a control system?
As I said, I think that the brain is an almost necessary control mechanism once you achieve a certain structure, a certain compartmentalization, a certain size. As soon as you have to optimize more than one function, it's not just get me away from this gradient or push me towards that other gradient or fight off that one bacterium. I now have to have many systems that need to be optimized. I need to trade off over a period of time. Maybe I'll trade off some liver function because the liver is very resilient. I might trade off some lung function, but how much I could trade off some gut function, but how much heart function am I willing to trade off, right? And so on. I mean, and they all do. There's phenomena that happen in every one of those organs that involve things like stunning and hibernation, where pathways are being turned off to limit damage, to retain energy. The system is doing a lot of adjustments to this, right? And my sense is that would not be possible without the brain. But it's also clearly possible at some level without the brain, right? So that the tissue is able to do it, but then to do it truly in a coordinated fashion, you need the brain.
You could do it with predefined rules, I could claim, as long as the system doesn't show hysteresis and memory. But if every challenge to the system leaves a trace of memory,
which it does,
then your predefined rules by necessity have to fail, because they can never take into account all these varying set points, right? So maybe this is the main reason why you would need the brain. But that would suggest then that your brain has to have a representation of these set points, of these changing set points. So is there any data that would support that?
Yeah, I think it does. I mean, in fact, just even observing the system and measuring key mediators, you can actually see a sense of this early hysteresis, which settles into a trajectory. In fact, we've got a study on this coming out very soon, hopefully. I mean, submitting it soon, that actually discovers in trauma patients, or using trauma patients, but something that we find in other systems as well, a regulatory architecture that we infer from having collected the data over time and modeled it as a network, and then encoded that hypothesis into a sort of a Boolean model, and then playing it forward and seeing that many qualitative and quantitative features of the system become reproduced from this. And it's a network that's bouncing up and down initially, so it's hysteresis, and it's figuring out, it's reacting. It's of course driven by the starting points of the system, which are individual specific. So people come into this with different initial set points. But if you run this simulation across time, you will see an early hysteresis, and then it settles on a trajectory, and you can map that to, I think you can map that to what might be what might be happening in different organs, and how the system responds as a whole.
Right.
Yes.
But now the brain control, how does the brain represent that system that is prone to get inflamed?
Yeah, so
what's the resolution of it?
So it seems like at least two key inflammatory mediators that happen to also be ones that drive this positive feedback loop are expressed in the brain in settings where inflammation is happening at a peripheral organ, either peripheral, like a peripheral organ alone, where you can give the noxious stimulus directly into that organ, and you can induce an inflammatory response that is not just spilling over systemically, but is staying fairly localized. The brain, in the area that also happens to control the function, a key function of, let's say, that organ, in this case the lungs, is expressing this inflammatory mediator. It's present in the lung, it's present in the brain, it's not just present everywhere, so it's not a giant diffusion issue. And the region of the brain also happens to be the one that regulates a particular function of that organ, and you can measure that function becomes disturbed.
That's the nucleus tractus solitarius.
Yes, the nucleus tractus solitarius.
But do you imagine that really as we have a somatosensory map of, let's say, the things we touch or in the properties of our muscles, you would imagine that I have a similar map representing all my organs and their inflammatory state.
Right. One could imagine even interesting, one could take a little flight of fancy and say things like acupuncture or acupressure that are based on the concept of meridians, are doing that. It's a manual way of creating that same thing. You create pressure at a distal location, which sends a signal to the brain, which can impact the liver, right? In martial arts, you have the ability to potentially strike a particular location in a peripheral area and have that translate to damage to the liver or the heart. So, intuitively, or empirically, people over the years have figured out that you can actually even use these methods for good or for bad. And so I think that is in fact how the system is wired. The system is wired so that there is a sensation of damage or dysfunction in a particular location. There's an impact, there's a sensation of that in the brain in a particular area. And then presumably, if that's above a certain threshold, there's a secondary activation of inflammation in the peripheral organ. One would like to believe that within a range, this is something that's evolutionarily beneficial for some reason. As I said, either that's because it's doing it in anticipation of there being a dysfunction that's going to occur in that organ, or an infection that's going to occur in that organ. And so there's a pre-positioning of defenses, or even a pre-starting of a healing program.
But also just be an artifact, right? Because
or it could be an artifact.
You have multiple somatosensory maps.
Yes.
And maybe, let's say, the liver in one map ends up to the lower arm in another map. But in the brain, they're close, so activity can spill over.
I could totally see that happening as well. And so then maybe that's when it becomes pathological, because now you're getting triggering for completely stochastic reasons, or just reasons that have to do with proximity. And now you get a secondary response somewhere else that now is no longer good. I would argue that when it does that, because of the closing of the loops, you end up having a compensatory response also driven by the brain to try to address that. Now, maybe that compensation is too much or too little, and that causes another problem. Maybe that's how things ripple. The point is, it's very interesting that, in talking to clinical colleagues. So, for example, a key phenotype that happens following severe trauma, or that actually happens following sepsis, infection, is that you get a severe blood pressure drop, right? In trauma, you get it because you're bleeding. In sepsis, you get it through secondary inflammatory mechanisms that create a blood pressure drop. The typical clinical response is to give fluids to raise the blood pressure, or to give pressors to raise the blood pressure. Because there's going to be, of course, an impact on the heart, they're going to use inotropes as well. But one might imagine that within a range, it would be best to leave the system alone, because the sensation of the blood pressure drop is itself triggering secondary corrective responses. The flooding of the system with information driven by an outside agent actually ends up confusing the system. The system now is unable to respond appropriately because it's looking for a set of cues that it just doesn't find, right? And now one could argue that critical illness is that. It's because critical illness cannot show up if there was no intensive care unit, if there was no, I'm not in any way trying to say that we shouldn't have medical care, but certain phenotypes are a consequence of the medical intervention.
It's an important observation, right? Because as long as you don't understand this complex network nature of the system, we're chasing symptoms, we might be only further destabilizing it as opposed to helping it to get back within the range of normal operation.
And I get a sense from my clinical colleagues that they often feel like that.
Mm-hmm.
Our study on the survivors versus non-survivors, which was followed of trauma, which was followed by another study we published recently, where we used that population to discover novel genotypes associated with survival and non-survival, suggests the possibility that some percent of the population is wired from the beginning to have this very rapid feed-forward inflammation, which in the context of, say, severe traumatic injury will lead to death.
Mm-hmm.
The suggestion is that and of course that is ethically scary, because the suggestion is that as things are, it will simply not be possible to rescue those people. The hope would be that the discovery of those early pathways that we've done through network analysis might lead to targeted interventions that can be given very early to reverse that, to change that. Right. Those pathways, by the way, are not, again, nothing in inflammation is ever just inherently harmful. Those pathways are pathways that would protect you from infection. So in normal daily life, the fact that you are overly sensitive sets you up for doing way better in terms of dealing with normal infections. But now, at the wrong time, in the wrong place, with a severity of injury above a certain threshold, those genetics set you up for progressive inflammation and death.
But in those situations, your only hope is to completely block communication between organs.
Right. So that's a very interesting point. So rather than, I'm an immunologist, so of course my normal solution is immune, but one could imagine that an appropriate stimulus given centrally at the brain level could in fact accomplish that, meaning allow the local environment to do its infection fighting thing if it can, while stopping the message that says keep cascading
break
forward.
the positive feedback.
Yeah, I agree.
Right.
The key is, of course, identifying those patients. Now, we now have a set of 7 single nucleotide polymorphisms that are interesting because not a single one of them is directly involved with inflammation, as we can tell, but are more with tissue health or resilience, if you will. We're completely predictive of the non-survivor phenotype. This needs to be validated again because we have overall only about 5% of patients will end up being non-survivors. In terms of people that make it into the intensive care unit, it's a larger percent if you look at severely injured patients that just are overwhelmingly injured, right? But 95% of patients can survive. So the idea is that, if one had the right biomarkers, and one had the right therapy that could be targeted in a very precise fashion, that should be quite doable.
Right, exactly.
Yes.
So, but then the other thing is now is the brain involved. The brain is controlling stuff, so we can be more dealing with complex, contextualized perturbations to the system. But now I'm going to pay a price because the brain is also screwed up.
Yes.
So psychological stress.
So one thing that happens already that can be observed in patients that are trauma patients, even if it's not traumatic brain injury, where there's, of course, a direct impact to the brain, is that you get into a kind of delirium state. Mm-hmm. There's a cognitive decline that is seen in severely injured patients. So that tells you the brain is, in fact, paying a price. Whether it's the assumption, I think, before was that it's an indirect process that has to do with the fact there's overwhelming inflammation, maybe a breakdown in the blood-brain barrier. But one could argue that one way in which you achieve that is because the brain is working overtime to try to regulate the inflammatory response, or it's getting now many centers activating with these inflammatory mediators that are both neurotransmitters and inflammatory mediators and have this positive feedback characteristic. So they rapidly spin up out of control in multiple places. Then one could imagine that could lead to at least a temporary cognitive impairment. One could also imagine that if over a long period of time, one has repeated stresses, repeated infections, repeated traumas, that the system again becomes overwhelmed and that sets you up for a chronic neurodegenerative disease.
But I wanted to push it deeper. The cascade, the causation in a direction, because yes, there's a lot of information that inflammation leads to neuropathology, right?
Yes.
For Alzheimer, Parkinson's disease, to many examples, right?
Right.
Or enough examples. But maybe it can go the other way around as well, that mental states rebuilt by the brain start to actually have an impact on the inflammatory states of organs in the body.
Yes.
That in the end lead to your demise.
Yes. No. And again, that is been very actively tested, and it's a very major area of not just investigation, but now of direct clinical application. There are companies that are directly stimulating the brain to be an anti-inflammatory mechanism or therapy for things like sepsis or rheumatoid arthritis or other sort of clearly inflammatory diseases. And it's not just by coincidence, it's because of this hypothesis, because of the data behind it and so forth. Yeah, and I think that's
what mental states can lead then to or amplify sepsis, aggravates as an example. What mental states would you call them stress, psychological stress, or would you call them something else?
I think that has been very understudied. The problem with sepsis is that although it is very much an acute inflammatory process and it can very rapidly spin up and out of control, the clinicians typically don't see the patient until that patient has been incubating this infection for some period of time, which can vary before they show up with severe enough symptoms to the intensive care unit. So it's very tough to be able to make that study. In trauma, the problem is that almost no trauma has zero impact on the brain to start with, right? Mm. So even if it's not a direct traumatic brain injury, there's of course, the massive sensation of the traumatic event. And then there's, of course, almost impossible to have the lack of any kind of anatomical impact on the head region. And have an injury severe enough to actually be having the symptoms one talks about. So it's, again, one of these very tough situations where I think it's there. I think it does do what you say, where someone pre-stressed. You could do epidemiologic studies. I think they have been done. But again, there's so many factors that go into that. There is this very interesting brain-related or apparently brain-related study in sepsis that looks at something that you would think would be quite a negative thing, so smoking. So it turns out that because nicotine itself can trigger, the nicotinic pathway can trigger anti-inflammatory mechanism, sometimes smokers actually are doing better in sepsis. You would think it'd be the other way around since they're having compromised lung function.
Right.
So of course one wouldn't recommend people to start smoking, but it's an intriguing sort of hypothesis. I think that, as I said, I think it would be quite likely that being in chronic stress will set you up for, it's known that being in chronic stress will set you up for infection. That's sort of known. Whether the epidemiology has been done to say that you could progress from that to full-blown sepsis, I don't.
But there's an interesting consequence of what you're saying now. It was the smoker example. In some sense, collectively we make this naive assumption that the healthy state is zero perturbation of the system.
Yeah.
It's this homeostatic view again. We're in stasis. But it is misguided because it's a dynamic system. It's a continuous change, and it's continuous change that maintains the healthy state in a range.
Appropriate responsiveness is held.
Exactly.
We showed that. So before we did all the modeling, we showed in trauma patients and also in experimental animals, the large animal swine model of severe injury and hemorrhage, that if you didn't mount an appropriate, adequately robust, say, inflammatory response, you would be a non-survivor, or you would be an animal that is not amenable to resuscitation. Mm-hmm. So a mediator that people would say, oh no, look, there's an inflammatory response, they're probably going to do worse. Actually, they're the ones that are doing well because it's a surrogate, it's a proxy for responsiveness. You can show that by measuring, norepinephrine. You can measure other, and they track with this. So the inflammatory responsiveness is just another way of saying responsiveness.
Right. So look, so for me, this is all fantastic also because I'm learning a lot, and it's also beautiful to see that this compartmentalization of been naively imposed on the system, like distinguishing brain from body from immune response, has been not very helpful, right? That's where these are very densely coupled networks. So now you're in this domain of immunology for a long time. You also have really been sort of advancing and struggling to bring new concepts and new ways of thinking into the field. So if we would like to follow in that tradition that you represent, what would be Yoram's law that we have to adhere to?
I don't know that would ever see myself as positing something like that. I would say that the best thing I can say is that inflammation as a communication network is something that needs to be looked at in pretty much any system that you're trying to study biologically. I don't really have a law like these are the exact underlying structural or functional motivations of biology or something like that. I'm just not at a place where I can say anything like that.
Of sort of the practice of doing science, the practice of gaining knowledge about this system.
Well, then that's much simpler. Yeah, I would say always interact with people from a different discipline and that think differently from you, and then try to integrate as much as possible. Don't have preconceived notions. I would say that is true. Yes.
Okay. So now I'm going to visit you in 4 years' time out there in Pittsburgh. I'm going to check the progress of research. As you know, research is hypothesis driven. So what's the hypothesis that you want to see confirmed in that 4-year time window?
So these studies that we've done that suggest now this temporal sequence of inflammatory activation bring up the automatic hypothesis that the innervation of those organs that are being activated in sequence has something to do with that inflammatory response. So then the logical study is studies in which you're doing selective denervation to the bottleneck organs, if you will. Selectively denervate.
Specific prediction.
So, for example, the spleen, selectively, it's one of it's essentially, we're seeing in mice at least that seems to be the place where inflammation reaches its peaks the soonest. The spleen is known to be, of course, very innervated. So selectively denervate the spleen, collect the time course data, run the network analyses, and see whether the networks that you've previously seen are now
Your prediction,
collapsed.
The spleen is the hub of inflammation
For this particular mouse model. So in this particular strain of mice that's tuned to be very inflammatory, and to this particular stimulus. Now we have an entire set of data that I didn't even talk about today, where we subjected the same mice, the same two types of mice, to experimental trauma hemorrhage, because it turns out that the beauty of this is the same receptor that's being used to sense damage-associated molecular pattern molecules in the case of trauma is the one that also is being sensed for lipopolysaccharide in the case of sepsis. So we could compare the two mice strains across time and across all the organs, right? But now the stimulus is quite different. It has a different characteristic. It's not a rapidly peak-shaped, influx of a very strong bacterial immunostimulant. It's now a combination of trauma with hemorrhage and secondary mechanisms, and all these organs do fail in the critically ill patients that have that.
How do you summarize it in a 10-word prediction we can print on a T-shirt?
For what's going to happen in the trauma hemorrhage? Yeah. I would say that in the trauma hemorrhage, we were going to probably see a much more central early role for the gut, which we saw a bit later in the sort of sepsis model. And but I think the bigger prediction is more that we will see networks collapsing when we denervate the bottleneck organ. Let's say the first organ that matters. We will see downstream networks collapsing, and that if we do the control study where we, let's say, denervate the last organ or somewhere in the middle, we're only going to see a partial collapse of those networks. Yes.
Wonderful. Yoram Vodovotz, thank you very much for this conversation.
Thank you very much for having me on this podcast and for inviting me to BCBT.
You're welcome.
Terrific.
Come back anytime.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.